4.5 billion years ago, the solar system was not the orderly clockwork mechanism we observe today. It was a demolition derby. Protoplanets, the massive embryos of future worlds, careened through the darkness, smashing into one another in cataclysmic mergers that would eventually forge the stable planets we walk upon. The most significant of these collisions happened right here, at Earth. A Mars-sized wanderer, a planetary embryo that scientists call Theia, slammed into the proto-Earth with such violence that it nearly destroyed both worlds. From the vaporized ruin of that impact, the Moon was born. For decades, this giant impact hypothesis has been the bedrock of lunar science. It elegantly explains why the Moon is so large compared to Earth, why it lacks a heavy iron core, and why the Earth-Moon system spins with such specific angular momentum. But for nearly just as long, there has been a gaping hole in the theory, a forensic inconsistency that has kept planetary scientists awake at night. It is called the Isotopic Crisis. If Theia was a separate planet formed in a different part of the solar system, it should have possessed a distinct chemical fingerprint, just as Mars, Vesta, and meteorites do. The Moon, formed largely from Theia's debris, should carry this alien signature. Yet for 50 years, every single sample brought back by Apollo astronauts shouted the opposite. They told us that the Moon is not alien. Chemically, it looks almost exactly like Earth. Today on G Fun Facts Online, we are going to trace the scientific detective story of Theia, from that initial isotopic crisis to the stunning recent breakthroughs of the mid-2020s. We will explore how new high-precision measurements of obscure elements like molybdenum and thallium have finally revealed Theia's true identity, and how a revolutionary discovery deep inside the Earth suggests that Theia isn't gone. It is still here, buried beneath our feet, forming the very foundations of our world. To understand the magnitude of the recent discoveries, we must first understand the problem that plagued the giant impact hypothesis for decades. In the solar system, oxygen is the standard of identity. Oxygen exists in 3 stable isotopes: O-16, O-17, and O-18. The ratio of these isotopes varies wildly depending on where in the solar nebula a planet formed. Mars has a distinct oxygen flavor. The asteroids in the belt have another. Comets have yet another. These ratios are so distinct that if you hand a geochemist a rock, they can tell you purely by its oxygen isotopes whether it came from Earth, Mars, or a specific class of meteorite. When the first Apollo samples were analyzed in the 1970s, scientists expected to see a mix. Standard models of the giant impact suggested the Moon should be composed of about 70 to 90% Theia material and only 10 to 30% proto-Earth material. Therefore, the Moon's oxygen signature should look like Theia's. Instead, the results were shocking. The Earth and the Moon were isotopically indistinguishable. To the limits of the most precise mass spectrometers available, their oxygen ratios were identical. This presented a paradox. Either Theia miraculously formed at the exact same distance from the Sun as Earth, using the exact same mixture of raw materials, the odds of which are astronomically low, or the impact was so violent that it vaporized both worlds entirely. This second option leads to a theory called a synestia, a donut-shaped cloud of supercritical rock vapor, where the gas of Earth and the gas of Theia thoroughly homogenized before the Moon condensed out of the fog. For years, the synestia model gained traction as the only way to solve the oxygen problem. As technology improved, scientists moved beyond oxygen to heavier, more refractory elements like titanium and tungsten. Titanium is incredibly stubborn. It doesn't vaporize easily. If the oxygen was mixed by a vapor cloud, the titanium should arguably still show differences if Theia was distinct. Yet, again, the fingerprints matched. Earth and Moon shared the same titanium anomalies. The crisis deepened with tungsten. Tungsten-182 is produced by the decay of hafnium-182, a short-lived isotope present only in the very early solar system. Because hafnium loves rock and tungsten loves iron, when a planet's core forms, the tungsten sinks to the center while hafnium stays in the mantle. The fact that Earth and the Moon share identical tungsten anomalies implies that their mantles have the same age and differentiation history. This was baffling. How could a small impactor like Theia have the exact same evolutionary history as the Earth? The deadlock began to break in the early 2020s, accelerating into 2025, as researchers began employing isotopic fine-tooth combs on elements that tell a different story. These are the nucleosynthetic anomalies. Unlike oxygen, which is fractionation-dependent and changed by biological and geological processes, nucleosynthetic anomalies in heavy metals like molybdenum, ruthenium, and zirconium are genetic tags. They represent the raw stardust mix, material forged in different supernovae that existed in the cloud before the sun was even born. These cannot be changed by melting or mixing. They are the DNA of the planet. In a landmark series of studies culminating in late 2025, researchers at the Max Planck Institute and Caltech analyzed molybdenum isotopes in lunar rocks. Molybdenum is a siderophile, or iron-loving element. When Earth's core formed, almost all the molybdenum sank into the center. The molybdenum we find in the crust and mantle today was delivered late, by the impacts that happened after the core closed. This makes molybdenum a perfect tracer for Theia. Since Theia hit Earth after Earth's core had started to form, the molybdenum in the Moon should represent Theia's composition, not the pre-existing Earth's. The results were a revelation. The data ruled out the theory that Theia was a wet carbonaceous body from the outer solar system. The molybdenum data showed that Theia had a non-carbonaceous signature, meaning it was born in the dry inner solar system, just like Earth. But the data went further. By comparing the subtle offset in iron and molybdenum isotopes, the 2025 study suggested Theia likely formed closer to the Sun than Earth, perhaps near the orbit of Venus or Mercury. It was an inner sibling, cooked in a hotter part of the nebula before drifting outward to collide with Earth. This solved the isotopic crisis, not by demanding a total homogenization, but by proving that Theia and Earth were made of the same stuff to begin with. They were sisters, born from the same band of the protoplanetary disk. While heavy metals proved the genetic link, volatile elements like potassium and zinc revealed the violence of the event. Recent analysis shows the Moon is drastically depleted in light isotopes of zinc and potassium compared to Earth. This is the classic signature of evaporation. When the impact occurred, temperatures exceeded 4,000 Kelvin. In this inferno, lighter isotopes of zinc and potassium boiled away into the vacuum of space, while the heavier isotopes were left behind to accrete into the Moon. This confirms that the Moon was born from fire. It was not a gentle capture of a passing body, nor a fission caused by Earth spinning too fast. It was a high-energy cataclysm that processed the chemical soul of the Moon, leaving it dry and depleted compared to the water-rich Earth. While chemists were hunting Theia in lunar rocks, geophysicists were hunting her using seismic waves inside the Earth. For decades, seismologists have known about two colossal structures deep in Earth's mantle, sitting just above the core. These are called the LLSVPs, or Large Low Shear Velocity Provinces. There are two of them. The Tuzo blob is located beneath Africa, and the Jason blob is located beneath the Pacific Ocean. These blobs are massive. Together they make up about 8% of Earth's volume. They are denser than the surrounding mantle and chemically distinct. Seismic waves slow down when passing through them, indicating they are hot and heavy. For years, scientists debated their origin. Were they just piles of subducted oceanic slabs? Or were they primordial piles of rock from Earth's formation? In a paper that shook the geophysics community, a team led by Qian Yuan proposed and modeled a startling hypothesis. The LLSVPs are the physical corpse of Theia. The simulation suggests that when Theia, which was roughly 10% of Earth's mass, hit our planet. It sheared off its own outer layers to form the moon. But Theia's dense, iron-rich core and deep mantle didn't vaporize. They punched through Earth's magma ocean like a bullet. Because Theia's mantle was denser and richer in iron oxide than Earth's, these fragments didn't mix. They sank. They fell all the way to the bottom of the magma ocean, settling on top of Earth's core. Over 4.5 billion years, mantle convection swept these fragments into two large piles, which we now see as the African and Pacific LLSVPs. This hypothesis unifies the chemical and physical evidence. The isotopic crisis is solved because Theia was chemically similar to Earth, having formed nearby. The missing impactor problem is solved because Theia isn't missing. We are standing on top of it. Synthesizing the latest chemical and physical models, we can now reconstruct the most accurate timeline of the moon-forming event ever assembled. 10 million years before the impact, Theia forms in the inner solar system, likely near the orbit of Venus. It is dry, hot, and differentiated into an iron core and a rocky mantle. Gravitational perturbations from a growing Jupiter or Venus destabilize its orbit, sending it spiraling outward toward Earth. Then comes the impact. Theia strikes the proto-Earth at a 45-degree angle at a speed of roughly 4 kilometers per second, or 9,000 miles per hour. The energy released is equivalent to trillions of hydrogen bombs. Within 4 hours, the collision liquefies the Earth's surface down to the mantle. Theia is obliterated. Its metallic core shears apart and plunges into Earth's core, instantly increasing Earth's density. A massive plume of vaporized rock, a mix of Theia and Earth, is ejected into orbit. Within 24 hours, the debris forms a disk. Volatiles like water, zinc, and potassium begin to flash boil away from the hot disk, escaping the system entirely. This baking process ensures the future moon will be dry and barren. Within 100 years, the debris disk rapidly cools and collapses. The moon accretes incredibly fast, perhaps in as little as a few months or years. As it coalesces, it is a molten magma ocean. Within 1 billion years, inside the Earth, the dense fragments of Theia's mantle settle at the core mantle boundary. They begin to shape Earth's convection currents, eventually driving the superplumes that will break apart supercontinents and drive plate tectonics. Theia, in death, becomes the engine of Earth's life. One of the most intriguing recent debates concerns water. If Theia was a dry, inner solar system planet, as the molybdenum data suggests, and the moon is bone dry, where did Earth get its oceans? The canonical view was that comets brought water later. However, new isotopic studies of ruthenium suggest that Earth's water was already here before the impact, locked in the hydrated minerals of the proto-Earth. The giant impact was a double-edged sword. It boiled away the surface water, but the atmosphere it created, a heavy steam atmosphere, may have eventually rained back down. Furthermore, the Theia blobs might play a crucial role in the deep water cycle, acting as reservoirs or barriers for water cycling through the mantle. Some astrobiologists now argue that the collision was essential for life. The sinking of Theia's dense material might have destabilized the mantle enough to kickstart plate tectonics, which regulates Earth's climate. Additionally, the merger of Theia's core with Earth's core added the heat and energy necessary to sustain our geodynamo, the magnetic field that protects our atmosphere from solar wind. Without Theia, Earth might have ended up like Venus, stagnant and hellish. We used to think of the moon as a separate child of the Earth, or a stranger caught in our gravity. The chemical evidence now tells a more intimate story. The Earth and Moon are a binary system, born from the fusion of two worlds. We are not living on just Earth. We are living on Earth Theia. The Moon is the splash of that union, frozen in the sky. But the bulk of Theia is down there, 1,800 miles beneath our feet. Every time a volcano erupts in Hawaii or Iceland, it is fueled by plumes rising from the edges of the LLSVPs, the ancient, hot remains of the planet that died to give us our moon. The chemical fingerprint of Theia is no longer missing. It is written in the stone of the moon, and it is beating in the heart of the Earth. The next chapter of this story will be written by the Artemis 3 astronauts. Unlike Apollo, which landed in the equatorial Maria or seas, Artemis will target the lunar South Pole. Here, deep in the shadowed craters, lie rocks that may represent the moon's deep mantle, material that has not been melted or altered by subsequent asteroid impacts. If we can retrieve a piece of the moon's pure mantle, we might finally hold a piece of unmixed Theia in our hands. Until then, we can look up at the moon and down at the ground with a new understanding. They are two halves of the same ancient catastrophe, a collision that destroyed two worlds to create the one habitable oasis in our solar system.